In this lecture, we are going to start looking at machine learning from a new perspective. While this example might seem overly simplistic, you might be surprised to learn that every example that we do in this course will rely on these basic steps which you are about to learn. First, let's start by describing the basic task. I'm sure you're all familiar with this example from your grade school science and math classes. Let's suppose we've done some kind of scientific experiment. For example, we measured the voltage in a circuit with different resistors, or we asked everyone in our class what their height and weight is. This gives us a dataset with two columns of numbers, one that we can call x and the other that we can call y. Now imagine that we plot these points on a grid and we get something that looks pretty close to a line. We would like to draw a line on this grid that closely passes through these points. In your grade school class, maybe you did something like took a ruler and moved it around a little bit until you found the best possible line. But now that we're doing machine learning, we need more sophisticated methods than just drawing dots on paper and using a ruler to estimate what the best line should be. The problem is, what happens when we have thousands or millions of dots? What if our data is more than two-dimensional? Then this approach is no longer possible. So perhaps you might say, aha, I know what to do. Let's use our trusty tool, scikit-learn. As you know by now, this is what a basic regression script might look like if we were to use scikit-learn. First, we load in some data, call that x and y. These would just be the two columns of data that we were looking at earlier. Next, we create a model. For the coming lectures, we'll be interested in linear regression, so let's create a linear regression model. Next, we call the fit function to fit our model to the data. Next, we can do multiple things with our fitted model, such as making predictions with model.predict. The problem with this is just using an API, but it doesn't tell us how any of this actually works. What actually happens inside these functions, and why is that important to know at this stage? What I want to highlight on this screen is what we should expect to be different when we look at PyTorch. First, model creation is going to be different. As I mentioned earlier, PyTorch is going to allow us to build all kinds of different models using composable building blocks. So it's not going to be some predefined model as in scikit-learn. Next, I want to emphasize in PyTorch, there is no such thing as a fit function or a predict function. This is unlike TensorFlow and Keras, which do provide you with those functions. So if you're looking for something simpler, then TensorFlow or Keras may be more your pace. In PyTorch, however, that will not be the case. Therefore, we're going to have to find out how to do all these steps in PyTorch using our knowledge of the concepts. Importantly, however, this lecture will focus only on the concepts and not on any PyTorch. In the next lecture, we'll look at how to actually implement these concepts in PyTorch syntax. So let's first look at what these concepts are before we discuss the details. I'm going to go out of order in some sense, but you'll see why that has to be the case. The three main concepts we want to discuss are, number one, what is the model architecture? And how do we actually build a model if it's not defined for us, like it is in scikit-learn? Number two, how do we make predictions with the model? In fact, this is closely tied to number one. And number three, how do we fit the model? That is, how do we find the slope and intercept parameters? As you'll see, this is the most complicated step. It also depends on number one and number two, which is why we have to discuss this last. So number one, what is the model architecture? Well, you already know this. It's y hat equals mx plus b. Notice our use of the hat symbol here. Typically, we'll use y for the true value, also known as the target, which is given in the dataset, and y hat for the corresponding prediction. Fortunately for us, this actually solves both of the first two problems for us. This not only defines the model architecture, which is a line, but it also tells us how to make predictions. Given some input x, I can see exactly how to calculate y hat. Pretty simple. So this is our model. Y hat equals mx plus b. The hard part is number three. How do we actually find good values of the slope m and the intercept b? The key is to define what is called a loss function. I warn you that there are many synonyms for the loss function, and you'll see them all, so don't be afraid if you see these different terms and think one of them might be wrong. That's not the case. These words are all used equivalently. So you might see this referred to as a cause function, or an objective function, or an error function. These all mean the same thing. The basic idea is this. If we pass in our data set x and y, along with some setting of m and b, the loss function will tell us how good that setting of m and b is. Let's see how. First, let's assume that we're given a set of pairs of data points, x1, y1, x2, y2, all the way up to xn, yn. Make a note to yourself now that it will be convention for us, and many others, to use the capital letter N to represent the number of samples in your dataset. This is not always the case, but it's at the very least the convention I use and the convention many others use. So if you see something different in the future, or you've seen something different in the past, don't freak out. Believe it or not, this happens sometimes. Anyway, the idea behind linear regression is, we will not find a line that perfectly passes through all the points. That's impossible since, as you can see, there is no such line that can pass through all the points. All we can do is try to find a line that is a good fit. So how do we define a good fit? As I mentioned, this is called a loss function. I'm going to start by telling you what it is, and then describing to you why it makes sense. For some of you, it'll make sense immediately, and for others, it might not. But hopefully by the end of this, I will have convinced you that it does make sense. So the loss function that we use in regression is called the mean squared error, or MSE for short. Basically, you take all the yi's, and you find the squared difference between them and the line itself, the y hat i's. You can think of this as the squared vertical distance from each yi to the line. Each corresponding point on the line is a y hat I, a prediction given xi. Once we have all the squared differences, we take their average. You all know how to find averages, so you know that it's just the sum of the squared differences divided by the total number of points n. The question is, why does this make sense? I think this is a great exercise to try for yourself if you haven't done so before. Take a piece of graph paper and draw some dots and a line, just like what you see here, and calculate the squared error by hand. What you should discover is that if the line is not a good fit, then the error will be larger. If the line is a good fit, then the error will be smaller. I think that's pretty intuitive. In addition, you should recognize that if the data points perfectly lie on the line, then the mean squared error will be 0. Next question. How do we use this loss function and our model to actually find the values of m and b? Let's see what happens if we plug in our expression for y hat into the loss. This is clearly the equation we would get. Now I have a quiz question for you. What are the variables in this equation? I'll give you a second to think about it, so please take a moment to come up with the answer before moving on to the next slide. Okay, so I hope you thought about the answer to what the variables are in this equation. If you said x and y, this is not correct. Many beginners make this mistake because in a typical math course, the variable is x, and you're always trying to do something like solve for x. However, it's important to recognize that in machine learning, x is normally not a variable. xi and yi are just values from our dataset. You can think of them as numbers from your Excel spreadsheet. In fact, in our case, the variables are m and b. Remember that these are the values that we are currently trying to find. They are unknown, and therefore they are variables. At this point, we know that our goal is to minimize the loss with respect to m and b. This is how we would write that mathematically. If you're afraid of math, don't worry about this equation too much because it doesn't give us anything new. It's just a way of saying what we already said, but using math. We would like to find the best values of m and b, called m star and b star, where these values of m and b are the ones that minimize the loss L out of all possible values of m and b. How do we solve such a problem? It might help to consider a similar but simpler problem. Say we have a function f of x equals x squared, a quadratic. We all know this from high school. You might say, well, I can just look at the graph and see that the minimum value is 0 when x is 0. But remember, we don't do that in machine learning because in machine learning, we work in multiple dimensions. You can't just look at it. At this point, we have to introduce our old friend calculus. If you recall, the way that we solve this is you find the derivative, df by dx, set it equal to 0, and solve for x. This is because, as you can see, the derivative at the minimum is equal to 0. So if you draw a tangent line at the minimum point, it should be a horizontal line. There are, of course, a lot more details that I'm not including here, but you should at least remember this from your high school math studies. So how do we find the solution in our case? Since we have two variables, m and b, we have to take partial derivatives. But the idea is the same. Find the partial derivative of L with respect to m and set that to 0. Find the derivative of L with respect to b and set that to 0. This will give us two equations with two unknowns, which are m and b, at which point we can solve for m and b. In fact, if you've never done this before, I would encourage you to do this calculation and solve for m and b as an exercise. This can be done for any arbitrary dataset, x1, y1 up to xn, yn, so your solution should be in terms of those values. There is a problem with this approach, however. Unfortunately, finding the derivatives and setting them to 0 only works for linear regression. It does not work for any other model we will discuss in this course. In fact, the very next model we discuss for linear classification cannot be solved in this way. Instead, we need to use a method called gradient descent. Very briefly, the gradient is the multi-dimensional analog of the derivative. So basically, when you're working in multiple dimensions, you have gradients in place of scalar derivatives. The idea behind gradient descent can be understood with this simple picture. It's an iterative algorithm, so we're going to go in a loop. On each iteration of the loop, we are going to take a small step in the direction of the gradient. It's been mathematically proven that if we keep doing this, we will eventually end up at the minimum point. In this lecture, I don't want to get into detail about gradient descent. However, you are encouraged to check out the lectures in the in-depth section of this course if you are interested. Our goal is to get to how we do this in PyTorch as quickly as possible. Gradient descent is a really cool algorithm because it works in pretty much all cases. That's why libraries that have automatic differentiation, such as Theano, TensorFlow, and PyTorch, have been so popular for machine learning. Aside from deep learning, you can use the exact same techniques for things like hidden Markov models, k-means clustering, matrix factorization, and more. Alright, so since this has been a pretty long lecture, let's recap the steps. Our goal in this lecture was to take you from the 3 steps of the scikit-learn API to what actually happens conceptually. As you recall, the 3 steps are creating the model, fitting the model, and making predictions with the model. After this lecture, you now understand at a high level what actually happens during these 3 function calls. However, the concepts don't provide the full picture because we still need to implement this in code. In fact, I have a course that goes very in-depth into all these concepts and how you can take them and put them into a computer program using basic libraries like NumPy in the Python programming language. But remember, this course is about PyTorch, so the next question we have to ask is, how is this done in PyTorch? Concepts are one thing, but syntax is another. For example, the syntax for PyTorch will be different from the syntax for TensorFlow, even if we are doing the exact same thing.